Hello again, physicists. Today's video is on the work-energy relationship. So we've already discussed that if there are only conservative forces acting on a system, it means that the energy within that system will remain the same. Only thing that can happen is the energy can change form. However, in the presence of friction, or if there's some sort of applied force that's doing work, basically a non-conservative force is present that will cause a change in the energy of the system. This means one of two things can happen. If the non-conservative forces are doing positive work on the system, it means the system will gain energy from its surroundings. If the non-conservative force does negative work, it means that the system will actually lose energy to its surroundings. So here's a little comprehensive example that shows where positive work is causing a gain in energy and negative work is causing a loss of energy. The example involves a roller coaster, and we're going to start with when a non-conservative force doing positive work will cause a gain in energy. So if you've ever ridden a roller coaster, you know that the first thing you do when you're going up that largest hill is there's a chain that actually carries the car up the hill. That chain is an applied force, so that's going to be a non-conservative force acting on the car, and the direction of that chain would be up and parallel to the incline of the hill. Now, while the chain does that, it is displacing our car in that same direction, noted here with the green arrow. So that tells us right off the bat that we have positive work being performed here since both of these things are in the same direction. So that means that there must be energy gained by the car, and that energy would be gravitational potential energy, because the car starts at a non-zero height and then ends up way up there at the top of the hill. So positive work from the chain has to be equal to whatever gravitational potential energy the car gained as it was being pulled up the hill. Once the car reaches the top of the hill, we know from just standard conservation of energy problems where the track was frictionless that whatever gravitational potential energy it had at the top of the hill, it would have the same amount of kinetic energy at the bottom of the hill. But let's change that situation. Let's make this portion of the track rough so that there actually would be some friction between the car and the track. Basically, what that would mean is whatever gravitational potential energy I have up here, I will not have the same amount of kinetic energy down here. In fact, it should be less. The reason is because friction is also a non-conservative force. It will do work on the car as the car travels down the hill. Difference here, though, is we know friction will work against the motion of the car, so friction would be pointing back up parallel to the hill, while the car is displacing itself in the opposite direction down and parallel to the hill. Now, because these two things are pointing in opposite directions, that means this would be negative work, and as a result, the car is actually going to lose energy as it is going through this patch of the track that has friction. And whatever the difference would be between the positive gravitational potential energy I have up here and the positive kinetic energy I have down here, it has to be equal to the negative work done by this frictional force. It's important to remember that this energy that's being lost by the car is not disappearing altogether. It's just being transferred to the surroundings, things like the track or the surrounding air. Usually, when energy is being transferred out of the system like this, especially if friction is the culprit, it's through the form of heat energy. So if we put numbers to our prior diagram, and let's say that at the top of the hill, the car had 1,000 joules of gravitational potential energy. That means the chain did 1,000 joules of positive work on it. And that when the car went down the track, at the bottom, it only had 700 joules of kinetic energy. So we have a 300 joule discrepancy. That means that the frictional force that was acting on the car as it went down the hill must have done negative 300 joules of work. And that as a result, the car lost those 300 joules of energy it had at the top of the hill, and it was converted into heat energy and absorbed by the surroundings. So this can be a very difficult concept for students to understand. We're going to spend probably a day, 2 days, just looking at various examples, getting a thorough handle on work-energy relationships. But until next time, physicists, until next time.